Yeah, thanks. Thanks for the introduction. Thanks to the organizers for the kind invitation to speak here. It's a great workshop. I'm really enjoying the talks and the discussions. So now I have the duty to talk after the conference dinner, which can sometimes be hard. So I wanted to talk about complexity in chaotic systems, or in more general a bit in quantum many-body systems. And so what is the idea behind this? Well, so I come from quantum simulation. And so in quantum simulation, we want to use quantum devices to produce states that are so complex in some way that we cannot do the same thing in a classical computer. And so while working on implementations, of course, there come naturally the question, so what actually makes a quantum system complex? Now we can go to Wikipedia and look up what is the definition of a complex system, and then you find this is some system of many components that interact with each other in some way. Okay, so then this artist's impression here means this would be a complex system because there are many degrees of freedom and somehow they interact, whereas this one would not be complex because there are few degrees of freedom and then maybe we interact only very weakly. Then one can look a bit more, some more definitions. And, so why are these complex systems interesting? Well, in general, they are complicated in some way. They have also nonlinear behavior. They are not necessarily deterministic. And what makes them especially interesting, I guess, is because they can also show emergent behavior that comes out collectively from these many degrees of freedom. Okay? But so this is in general a complex system. So now what makes a quantum system complex? Okay, so especially in a way that is different from a classical system. And so what is quantum about a many-body system? Well, then one can think, okay, of course, the quantum system has to be entangled. Huh? Entanglement has to be in there. And indeed, if you look back at this inspiring talk by Feynman in 1982, there he says it very clearly that we need entanglement. So he talks about the Bell inequalities. Well, so he talks about non-locality, there's the subtle difference, okay? But let's put this under the carpet. So he talks about the Bell inequalities and then says, that's all, that's the difficulty. That's why quantum mechanics can't seem to be imitable by a local classical computer. And so indeed, if you have a many-body system that is highly entangled, we have many, many states that are in the superposition. And so the computer needs to keep track of all these states. And that makes it very hard for tensor networks. Now, but this is not the full story. There are highly entangled states that are easy to describe. Classically, one paradigm example is the ground state of the Tori code, which looks very complicated. It's a very high superposition, but actually one can describe the state simple. And the way how to do this is to use the Gottesman-Nil theorem. Here, I'm very thankful to Lorenzo, who on Monday already had a very nice introduction on all these things. But I think it's still nice to repeat some of these, to remind ourselves. Yeah? Okay, so what does this Gottesman-Nil theorem say in essence? Well, it says the following. If I have a quantum state that I can generate from the vacuum by a unitary operator C, and now C is not any unitary, but it's actually from the Clifford group. So I build it from C naughts, Hadamards, and S gates. Then this state, well, first of all, it's called a stabilizer state, and this is easy to compute classically. So I put here some circuit, randomly putting some gates from the Clifford group. So I don't even know what this computes. I don't take it too seriously. But this looks quite complicated, but in fact, it's very easy to describe classically using the stabilizer framework. And well, in fact, from using these, one finds that you can generate many states, but it's a discrete set and it's countable. And in fact, this is not enough to do universal quantum computing, which you can already imagine. If it's easy to describe classically, and we believe that quantum computers do something more than classical computers, then if this would be universal, okay, why would we do quantum computers? But indeed, this is not enough for universal quantum computing. What we are missing is, for example, the T-gate. So I just want to make a note for later when we then quantify this, if you're in a stabilizer state or not, one can realize that if you take a Pauli string, so a tensor product of Pauli matrices X, Y, Z, or also the identity. Applying such a unitary to that, it puts one Pauli string into another Pauli string. Okay? Not a sum of Pauli strings, but a single Pauli string. And so then if we use this definition up here with this property, we see that if we evaluate the Pauli strings in the stabilizer states, it's just we rotate things and it's like evaluating a Pauli string in the vacuum, which means that the number of Pauli strings that can give non-zero values is limited. No, for example, if you have an X, then this gives immediately a zero expectation value here. This one then can use to quantify if you're in a stabilizer state. Okay, but for now, I just want to point out another thing here, which I find interesting. That so the T-gate it generates non-trivial phases, and again, so I see this a little bit in complementary to entanglement. Now, entanglement tells what are quantum properties, while superposition is a quantum property. Okay, so entanglement tells us how many states do I have in the superposition. Here, this property here tells us what are the interesting phases in the wave function. So it's a bit complementary point of view. This one, yeah, we can think of it all down. So well, I dropped here the tensor, and so it's just all, yeah, exactly. Okay, so now we can sprinkle in some T-gates in here, and then one finds if one does this well, and now it becomes a generic unitary, it becomes universal, and in fact now this becomes difficult for classical computers. So using the stabilizer framework, one can show that the difficulty to simulate now this circuit here, or to generate this state, let's say, reproduce it on a classical computer, scales exponentially with the number of T-gates that you have in the circuit. On the other side, these T-gates are also those that are the hardest to do if you think about a fault-tolerant quantum computer using the surface code, for example, because you cannot do them transversally. We've also seen Julia's talk yesterday. Okay, so this I find quite interesting. As the T-gate on one side, it says for this specific paradigm of classical computing, it becomes hard. For this fault-tolerant paradigm of quantum computing, it becomes also hard. And I think, again, there's a parallel to entanglement. If you have a highly entangled state, it becomes hard for tensor networks. And on the other side, it's also hard for NISQ devices where the CNOT gates are the limiting factor, so the entangling gates. So both so they quantify hardness in specific paradigms. And so when I talk about complexity, I'm going to talk about, let's say, the build-up of entanglement and the build-up of this it's called non-stabilizerness, so the deviation from the stabilizer states. And of course, there are many notions about what one can call complexity, and which are also valid, and maybe even better notions and so on. But I'm using, if I talk about complexity, I mean this in this sense here. Essentially, the amount of entanglement and the number of T-gates. Okay, and so this is a very well-defined meaning of complexity, because you can really build a quantum resource theory that rigorously quantifies how useful is a state for quantum computing, which was introduced in this. Okay, so the questions that I want to shed a bit of light onto in this talk are, well, first of all, so which quantum many-body states are complex in this sense, in these resource theories of entanglement and non-stabilizerness? And then related to this, so are there, so to say, sharp boundaries between complex regions in this sense and non-complex regions? And so on, how do these behave? And then towards the end, if I have some time with this, I also want to talk a little bit about the two related questions, maybe. So once we know what are complex things, can we actually do them in experiments, and can we propose quantum simulators for these? And then also, can we use these complex states in quantum technologies? The arena where I'm going to discuss this is actually in the transition between ergodic and localized states. So again, you can look at the different many-body systems. We chose these things here. Where the intuition is the following, that if you have a completely ergodic state, then somehow all degrees of freedom are involved. So this should be complex in this sense. Of course, there might be emergent degrees of freedom that allow you to describe this in a simple way using a different computational paradigm. So that's not excluded, but in this sense that all are interacting and generate lots of entanglement and maybe lots of phases, they should be complex. And on the other side, if the system becomes localized, then only few degrees of freedom are involved, only few states are relevant, non-complex. And so if we have some tuning parameter, we're going to see in a second what this is, between the ergodic and the non-ergodic regime, and maybe there's a transition in between, then we can wonder what does this magic non-stabilizerness and entanglement do? Well, here it should be large, here it should be slow, but how does it behave in between? So does it go down just gradually? Does it have a sharp transition? Is it a plateau and then it goes down? And if there's a sharp transition, does it coincide with the ergodicity transition? Yeah, no, this is very model dependent. Absolutely, yeah. I'm going to introduce, so the next slide has the model that you're looking at. And then indeed, this is what I was trying to say also, know that you can have emergent degrees of freedom and so on. So this, I mean, it depends on your model, on your, also yeah, absolutely. So here, the criterion for complexity that I'm using is so it's how entanglement scales and the magic, this non-stabilizerness in the system. Okay? So it's for, let's say, for a specific paradigm. So if you say, okay, I want to do this with tensor networks, taking the computational basis. It's always basis dependent. It's also, I'm going to comment on this later. So I want to do this with tensor networks or with this stabilizer formulas, and then it's complex. And indeed, I mean, it could be that if you say, this is very complex, but then someone, so if it's a free Fermion theory, then maybe in reality, it was not like, okay, I can solve another method. Yeah, here we are going to talk about energy eigenstates, yes. And then it's also, it's model dependent. So, yeah, so I think it's, so what I'm aiming is to shed some light on this, what can happen, but I'm not saying that that is a full answer to everything. So the models that we are looking at is first random matrix models, the Rosenzweig-Porter model. And then we are also looking at the SYK plus Ising model. We also have another random matrix model, but I'm not presenting this here. Okay, and then later, so let's see how I'm doing with time then. Maybe I can talk a little bit about the quantum simulation of the SYK, which is going to be in this complex region in this sense, and complexity in quantum optimization. Let's see if we're doing with time. Okay. Okay, so let's start with the complexity transitions in the Rosenzweig-Porter model. Okay, so what is this model? This model is a random matrix theory. So you have a Hamiltonian is a matrix whose elements you fill in like follows. So you put in random Gaussian distributed values on the diagonal and also on the off diagonal, but now differently from a usual random matrix, there's a prefactor in front that scales down these off diagonals. Now, when you draw the Hamiltonian as a function of this parameter gamma, we see that when gamma is equal to 0, this is just a usual random matrix model, so all entries have a similar weight. And then as gamma increases, the off diagonals become weaker as compared to the diagonal. And so the phase diagram of this in the sense of chaos, ergodicity is already known for a long time. So here it's clearly, I mean, this is a random matrix, so we know that's a Wigner-Dyson level distribution. On the far side, when gamma is very large, well, the off-diagonals don't count anymore. You just have Gaussian distributed diagonals. So you're already in the diagonal basis. You just have a Gaussian distribution of the energy levels. And then in between, there's a transition from the ergodic to a non-ergodic regime, where the states are still delocalized, and then there's a further transition to a fully localized system. Now to analyze this, exactly. So the markers that we look at, this is the inverse participation ratio and the fractal dimension are those that are studied for a long time already in the system. So the inverse participation ratio looks at how the wave function is distributed over the basis states. And then the fractal dimension essentially just takes out, so it takes a log of this and divides by n. So if the inverse participation ratio scales exponentially, let's see if d is equal to 1, then this means it scales exponentially, all states are involved. If d is 0, then this becomes a constant. So there's only a small fraction of the states that are involved. And in between, if d is something between 0 and 1, then one calls this a fractal system. Okay? So this, yeah, so L is equal to n. So L is the dimension of the Hilbert space, and n would be the number of qubits equivalent. Okay, so this is where this phase diagram comes from, actually. And now we wanted to confront this with, on the one side, entanglement. So we take the half-chain entanglement entropy. And then, as I said, so this is somehow the size of the superposition and also the hardness for tensor networks, or the number of CNOT gates, if you wish, that you need to generate such a state. And we also want to confront it with the stabilizer Renyi entropy. Which is defined like this. Also, Lorenzo defined it on Monday. So one takes the expectation value of the Pauli string in the state of interest, and then sums over all Pauli strings. So this gives a probability distribution. You take the log of this, and then this gives a Renyi entropy in the probability of the probability distribution of these Pauli strings. And okay, so for the stabilizer states, when you think back of what I said in the introduction, there are only certain non-zero values. So if one plugs this in, one sees that the non-stabilizer Renyi entropy, the stabilizer Renyi entropy becomes 0, and it's non-zero as soon as we have some T gates in there. Okay, so one can say that this gives the difficulty in the sense of the Gottesman-Nil theorem, and it's also related to the number of T gates that we need to produce the state. Okay, so now let's see what these things do in this RP model. So now what we do is we tune the parameter gamma here from 0 to 3. And here we look at the bulk. We take the central 10%, but you can take also, this is very stable. You can take also 20 or 30 or whatever, as long as you stay away from the boundaries of the spectrum. Okay, and then so we can look at the fractal dimension, and so we see that, so we reproduce in essence things that are already known. We see that here the fractal dimension goes to 1, so the inverse participation ratio scales down to the system size, so essentially all states are involved. This is a fully ergodic system. On the far side, the D2 becomes 0, so inverse participation ratio becomes constant. There are only few states that are involved. It's a localized regime. And in between, we see that D takes a value in this fractal range. So this means that many states are involved. So it's delocalized. Many states are involved, but it's still not all states are involved. So it's not ergodic. Okay, now here, since this is a finite size system, so this is, by the way, this is the 2 to the 12, for example, dimension, okay, of the matrix that we're looking at. So so it's still relatively smooth. So one can do now scaling analysis. One way that we looked at this is by taking the derivative, and then we see how the derivative behaves, and we see indeed that here, essentially, if you look at it, the derivative goes to 0 in this regime, it goes to 0 in that regime, and to a non-zero value in between, which means that in the end it will be flat 1 here, then it will have a slope, and then it will be flat at 0 again. To do the scaling to infinite system size. It means that indeed, so here in this entire regime, the dimension is 1, it's ergodic. In this, from 2 onwards, in the thermodynamic limit, the system is going to be localized, and in between, it's going to be fractal. This reproduces already known results. Now we can do the same analysis also for entanglement and non-stabilizerness. And you see that they behave quite similarly at first sight. But then if you look more closely, so we can do the scaling analysis also here, you see that, well, these plateaus, they don't agree. So there is somehow a region, yes, of high complexity. So here all these take Haar random values, and then it goes to a lower complexity region, but these plateaus do not agree. And so maybe to draw, just because that's difficult to see, so the result of the finite size scaling looks like this. So in this orange regime, all these quantifiers scale at the order of 1, which means, so there's extensive magic or entanglement entropy. Okay, so this is high complexity. They take Haar random values in these regimes, and here they scale down with the system size. So this is low complexity. And the green one is this intermediate fractal regime. And the thing that we see is that, well, these transitions that we extract, then these are the uncertainties from our extrapolation. We see that these things that we extract, they do not coincide. So it could suggest that there is somehow a regime of intermediate complexity where the system is non-ergodic and delocalized, but it's still massively entangled and has a large amount of magic. That's a very good point. Yeah, exactly. This was exactly the comment that I was going to do now. So we have seen on Monday Lorenzo's talk, no, where he says, okay, magic. I mean, this is all basis dependent, no. Also the same for entanglement, no. But so we can do, let's do local rotations of the basis and see and take the minimal one that you can do, and then this could shift. Yeah, this we did not analyze it, but I think this would be a very interesting question to try to make this more general and also look at different measures. Absolutely. Yeah, exactly. That's yeah. Okay. If you say it like this, yeah. Okay. That's well. If you do them locally, probably not much will happen, no? Because I mean, for example, yeah, there's a slide. For example, if you look here, they cross at slightly different points, and this is we extrapolate the crossing point to the thermodynamic limit, and this is where we say there would be this critical point. Yeah, I mean, some basis rotation, of course, can change. Now, if you look at the fractal dimension, if you allow a full basis rotation, we can of course diagonalize the Hamiltonian, and then we're always localized in the eigenbasis. No, so there's but if you do local rotations, then probably nothing happens. So the same should, yeah. Okay, I'm not sure how much it can change. Maybe a little bit. I would assume that if you allow some unitary, that it can shift around. So around here, no? Oh, the entire one. Yeah, I'm not sure, because here in this regime, it really reproduces a random matrix. So if you do only local rotations, I'm not sure how much you can really change the behavior. Yeah, exactly. So qualitatively, I think it. But I think this would be a very interesting thing to think more about. Yeah. Yeah, exactly. Here it's all-to-all Hamiltonian. So there's no, I don't know, accepting the basis, the energy eigenbasis. There's no real preferred basis, because it's completely random. Okay. Okay, so now we're trying to understand if this thing is a general feature. So we also looked at the ground state. So we do the same thing, but now we focus on the ground state of this model. And what you can see is that the transitions are much sharper. And in fact, here we cannot resolve from our scaling analysis this intermediate fractal regime. So it may not even be there. We also see that instead the transition is not at 1, but it's shifted earlier. So there's a mobility edge, which is known from some random matrix model that can happen. So, okay, so we also see this here. And then, as I said, there's no intermediate fractal phase as far as we can tell. And what also happens is that all these 3 markers, they appear to be consistent. So there's slight deviations, but within the error bars, they could all lie at 0.7. And so now one can wonder, if you go back and you looked at this sort of phase diagram, we saw that these shifts, they happen in this intermediate fractal regime where we have non-ergodic states, but they're still delocalized and massively entangled in massive magic. So we can imagine that if this intermediate regime disappears, then all these 3 transitions should maybe coincide. And this is indeed what we see. And so there's the question, is this a consequence or is it a coincidence? This would require more analysis. We also see a similar behavior in the power law random banded matrix model. Okay, so maybe we try also to look at this in other models. And indeed, so yes, we see this behavior there, but it's still a random matrix. So one can ask, does this also hold, or can we transfer this analysis to other models that are not random matrices? So we looked also at the SYK plus Ising model. So the SYK, the Sachdevier-Kitaev model, just to remind ourselves what is this? Well, this is an interacting model. We have a many-body model. We have 4 Majorana modes that interact with each other with a completely random interaction strength, which is taken from a Gaussian. So this is an infinite range, all-to-all interacting system. And in some sense, one can say it's okay. It's sort of similar to this random matrix. There's all infinite range and so on. But I mean, if you write down the Hamiltonian for this thing, it's a very sparse Hamiltonian. So I see it somehow as an attempt to try to build a random matrix from a many-body system. And it's a very interesting model that you may have heard of. So at low temperatures, it saturates the Lyapunov exponent because it becomes as chaotic as allowed by the Schenker-Stanford bound. If you look at the out-of-time ordered correlator, it scales exponentially. So it's information, if you put in an excitation in the system, the information is spread over the entire system as fast as allowed by nature. And so this, and let's one think, okay, this behaves similar to a black hole. If you throw information at a black hole, it absorbs it as fast as nature allows. And so one assumes that this is a holographic dual, so a boundary theory that is dual to the bulk in Jakiv-Teitelbaum gravity. And one can make this also more rigorous by looking at Green's functions and action and so on. Okay, and on the other side, this has also been used a lot as a phenomenological model of strange metals because it's so strongly interacting that there are no quasi-particles in there, and it has an emergent conformal symmetry. So it also works as a toy model for a quantum critical system. Okay, now this is very interesting, but we wanted to tune away from there. So we add an Ising Hamiltonian. Okay, so we have a parameter lambda that interpolates between the SYK when we are at lambda, or it should be lambda here, when you're lambda equals 0, and it goes to the Ising Hamiltonian when we are at lambda equal 1. We can write down, using a Jordan-Wigner transformation, the Ising interaction in terms of Majoranas, and then this all-to-all interacting model on the other side becomes a local model with just nearest neighbor hopping, so to say. And so this can be seen a little bit in the similar spirit as the random matrix that has all-to-all, so all the off-diagonals are there, and then you tune down the off-diagonal. So here we have the all-to-all interaction, and this sort of shift something that is only local as compared to the off-diagonals. And just to point out, there's been a similar analysis as we are doing in this recent work by the group of Alyosha Hammer. But they looked at the interpolation between SYK4 and SYK2. So this is again the same, let's say, phase diagram. As we tune lambda, we start again high in all these values. There are a few subtleties. The stabilizer Renyi entropy, for example, we see that it's very sensitive towards actually the number of modes, because one can show that it has the symmetries of GUE, GOE, or GSE depending on the number of modes. So it reproduces a different random matrix theory depending on the size of the system. And but you see also this difference. This goes away as system size increases, so these curves get closer and closer, and it goes to the Haar random value for large system sizes. And the second thing that we observe is that there is indeed a high complexity regime, but it extends a bit, but it also seems to scale to smaller systems, smaller values of lambda as the system size increases. So this has a certain finite size stability, but it's probably not an extended phase. But in infinite systems, this should probably become just a pathological point at 0, and then it goes down very abruptly. So we go immediately from this high complexity regime to a low complexity regime, probably. This actually, so it's consistent with what we know about the holographic behavior of these models, because if one adds a single particle term, there's some finite size stability, but in large systems, a small single particle perturbation on the SYK brings you away from this holographic and very nice behavior. And so it could be interesting to connect this behavior here also to this holographic behavior. Again, what we see is there's no, there doesn't appear to be an intermediate fractal phase, and also so the transitions, they're roughly consistent within the error bars of all these 3 markers. So this seems really to be a pattern here. The model? This one is lambda, yeah, exactly. These are Majoranas, and this is this lambda parameter. Yeah. We looked a little bit at this, I think, but no. So it should also, so at least, so let's say from my expectations for a finite system. We should still see in this regime the usual dip ramp plateau behavior for finite systems, but then probably we will see as soon as you have a little lambda that it goes away. As you go to the localized, essentially, sort of localized regime. But for finite systems in this regime, you still should. You don't get Yeah, let's. Yeah, I mean, let's say it differently. So in the regime where you can see it, will shrink, no? It will be less pronounced as system size increases. How am I doing with time? Plenty of time. Okay. Including questions, okay, no, not plenty of time. Okay, I just make it brief. Okay, so now, okay, so okay, we see that there are these interesting regimes, yeah, where all these values essentially saturate the random value. And so we can wonder, so now, okay, if you say this is the interesting regimes that I want to reproduce, can I actually build this in a many-body system in a laboratory experiment that reproduces this? And so this is a work that we have been trying to do, or that we're doing for a couple of years now, to think about how one can realize the SYK model in cavity QED. That's a collaboration with the group of Jean-Philippe Brantu, who is really the person, the experimentalist who has started this, because so he really wants to do the SYK model in his setup and has pushed us to think about this. And it's also with Julian Sonner's group in Geneva. Okay, so just I'm just going to give you an idea. Okay, so it's just very roughly what are the ingredients, because we don't have the time to go through the calculations. But so the setup is essentially, you think about a cavity with different photonic modes, and in particular about the multimode cavity. Then one can also forget about the multimode cavity and do a sort of a trotterization, which we have described in this newer paper here. But so the calculations are sort of the same. Okay, so there's a multimode cavity, so there's the internal electronic state of the atoms that are trapped in the center. They can exchange excitations with the cavity modes. This is described by this Hamiltonian here. So you go from ground to excited, and then you absorb. By doing this, you have to absorb energy or a photon from the cavity. And then what we do in addition, we add in a classical drive, which is then going to define our energy zero, so to say, so the detuning of the cavity modes here relative to the drive. And then what the drive does, it allows us to go from the ground state to the excited state by taking out photons from this classical drive, so from the coherent state. Okay, and then there's also a detuning of this excited level. Now, okay, so these are the interaction vertices, if you wish, corresponding to this. You go from excited state to the ground state and you emit a photon, or you go from the ground state back to the excited state by taking something out of the classical drive. Okay, this is known things, and Anna Maria told us also about the cavity setup, so the similar things appear there. But here we want specifically to have this SYK interaction. So one way to do this is to imagine that to put in an additional blue light that generates a speckle pattern, which off-resonantly goes to the excited state, couple this to another auxiliary state. So we get a Stark shift here. And now, because this is spatially random, the detuning to the excited state will depend on the position. So all these delta D becomes a position-dependent thing. Now, if the detunings are large, one can do perturbation theory. So we can take these interaction vertices and stick them together to the resonant things, which are ground states come in and ground states go out. So it's two levels of perturbation theory, so a fourth order process. It's small, but it seems that the values work out, that we can just observe some interesting physics. And yeah, so we go from the ground state to the excited state. We emit a cavity photon. It's caught again. Then we go by going to the excited state from a different atom, and then we go back to the ground state by coupling to the drive. And here, these detunings to the excited state, they are disordered. And this, if you now let's look at this this vertex in an effective way after doing perturbation theory. This interaction has some disorder there. Okay, so now let's say, okay, this hopefully this is nice. Yeah, so this is why we need the many modes, because we need this is a summation over many modes here, or over the trotter. It's a no, they don't factorize. It's a sum over m, ijkm, iklm, and then this entire thing doesn't factorize anymore. Jij is sum over m, and then here you have some overlaps ij m ik. So these can be the different modes, or if you do it in a trotterized way. Yeah, exactly. Exactly. So it's a multimode, or if you do it in a trotterized way, so you cycle through spectral patterns, then in a time averaged way, you can also get. Absolutely. This is crucial because otherwise we reproduce, so to say, known physics. Yeah. And indeed, this number of modes that enter. Maybe I jump over this briefly. So we go to the SYK behavior is as we increase the number of modes that enter there. So if we don't, so the spectral form factor, for example, becomes the usual SYK one or the OTOC. Just one comment. So we computed actually this. Yeah. So it's so you can write down. So that's an extension of the SYK with complex fermions, which corresponds to a charged black hole and so on. So it's okay. Yeah. So this I think even in Sachdev's paper that he describes both versions. And so okay, so then we did also a first principle analysis to see if this is really we really get random Gaussian terms. And indeed, so we found that they are random. Indeed, so these are the distribution. But we actually saw that they are not Gaussian, but they follow a Cauchy distribution. And as we spent like 4 months or so wondering about this, tuning all the parameters, and saying, okay, we want the Gaussian distribution. Why is it not coming? There's also other papers that did proposals previously, and so there are many proposals before on SYK model, of course, on different platforms. So you can go to our paper and look at the citations in there. But so these previous proposals, usually they just made an argument of large numbers and said, okay, there's something random, we have many modes or many things, and so it becomes Gaussian. And so then we said, okay, so we need to reproduce a Gaussian, and it was not coming, and we tuned with all the parameters and everything. And then we realized that actually other papers, these also they get Cauchy distributions. So there appears that there are some correlations still in this matrix that avoid you from being fully Gaussian. And then you can wonder, how much does it matter? That becomes an interesting research question to wonder, okay, so we want to produce this highly complicated model. How precise do we actually need to be? So what can we allow ourselves to change? If we change the probability distribution a little bit, is it still holographic and all these things? Yeah, so this, I think this also, there comes an interesting interplay between theory and experiment. No? So this thinking about the experiment inspires us to think in new ways about the theory of this model. Okay, then we benchmark these things, it works. The nice thing is that this physics for the OTOC, for example, is just a few J, so this one could hope to observe. And what we're currently working on is to work out what can we actually measure in this setup. So can we also measure entanglement or magic even maybe? And another thing that we're working on, which also Anna Maria pointed out as in her talk as the elephant in the room. I was almost copying the slide here. Is that so we have we didn't really do the simulations with dissipation. We know what the dissipation does, how it looks formally. It looks weaker than the coherent parts, but of course then the cooperativity comes in and so on. So there's something that we're analyzing right now, what the dissipation does, and if you can still observe the K physics here. The density of states, we did many analyses this already a few years ago. I don't think we looked at the density of states. That's, okay, now I think I'm running out of time really. Mm-hmm. So you're referring to the Brownians, okay? So I think one could, in principle, also. So first, one could, in principle, also think about implementing Brownian SYK here, because you could quickly change the spectral pattern and things like this. Yeah, then about so there you say for Brownian SYK, it's known that the distribution doesn't play a role. I think it's also here, this folklore that we need a Gaussian distribution. I think it comes also for a commodity, because then we can do, in the large n limit, we can do the path integral analysis and so on, which, if the distribution is different, becomes significantly more difficult. But I think it's the essence. I mean, people like, I think Kitaev in his first talk even, he said, okay, the distribution doesn't matter too much. So I think people know that. Yeah, no, so it's something that we've vaguely in the back of our minds, but not actively worked on. Yeah, Brown, yes, okay, I agree. It's interesting. Okay, now I think I'm going to jump over this because we run out of time. But you also, very recently, this is going to be on the archive on Monday, maybe. Huh? So if you're interested, look at this. We looked at non-stabilizers in quantum optimization. And there's also interesting behavior. I'm just jumping over this. As you do the quantum optimization, we see that there's a sort of a magic barrier. As you start in very low magic states initially, and then you want to optimize your state. You want to go back to a classical solution, so you go back to a small magic state, but in between you go through a high magic state. And so this final magic correlates with the solution quality, and there's something that we can call a magic barrier that you have to go through. If you want to find a solution in the end of your algorithm, you have to build up magic and then get rid of it. And we also find that there's some interesting scaling behavior, which we are not yet, so this is like an observation. We're not yet completely sure what this means and if we can make something more out of this. For now, it's an interesting observation. We see that this holds for Q bits and for Q trits. So it seems a very general. And also if you do adiabatic, it's just a teaser. But I now want to summarize because I'm really out of time before the chairman gets too nervous. Okay, so we have studied this random matrix theory and SYK models through the point of view of entanglement and magic, and we see that there are these interesting transitions where it's first completely random up to some point, and then it abruptly starts to drop. So it's really like a critical behavior. And there seems to be a region in this fractal phase where we have some sort of mixed complexity. Okay. And we see that there's also ideas to generate some of these interesting models in experiments, and we're looking at if there's a connection between. Okay, we know that magic is important for quantum computing. Is it also important specifically, or how specifically does it enter quantum annealing or quantum optimization? And with this, I want to thank the team. So in this works, there are many people involved, and also thank you.